so I want to recall what they are. So this is a vector field in R3. You have three components. All x, y, z components are defined by scalar functions. So if I say vector field, in your mind you have to have a picture of a family of small arrows pointing to different directions at each point. Are you with me? So this is the mental picture of what a vector field is. And we say a vector field is conservative. If the following system of equations are true. So let's say I take a f sub y to be equal to gx, right? So we're taking the symmetric differentiations here. So f derivative with respect to y should be equal to the y component derivative with respect to x. So f z should be equal to hx, and the last one is g of y is equal to h of y. Okay, so three equations have to be valid simultaneously in order to make this vector field to be conservative in R3. We also have an easier version. If your vector field is in R2, you only need to worry about the first equation, right? So for f to be equal to ft is conservative. If f sub y is equal to g is x, right? So if your vector field is living in R2, it's much easier. You only need to verify one equation, and that's that. And both of these two conservative vector fields will be able, you can write it down in terms of the gradient vector field, am I right? Yeah, gradient vector field. So this f will be equal to gradient vector of a scalar function. So phi here is just a number function. Okay, so our very first job, after we define what a vector field is conservative means, is to determine a given vector field is conservative or not. If it is conservative, then we are looking for this potential function, right? There are some vector fields you can easily write down what the potential function is. For instance, I give you this function, and it's equal to 2x, 2y, 2z. And these kind of functions have the special property that these components are all dependent on the corresponding variables. All right? So x component is only involving x, y component is only y, z component is only z. And you can easily write down the potential function by finding the antiderivative for each component corresponding. All right? And then you just add them together and put a constant over there, and you're done. And this one you can really write down the potential function is equal to, what is it?
X squared.
X squared plus y squared plus z squared, and I want to stick in a constant here. And then you take the derivative. You can easily check this is indeed the gradient vector of this potential function. So finding the potential function, I highly suggest you to check. So this one is too easy, but still, it takes very little time to check because you're taking the derivatives. Taking derivatives is always the easier method, right? It's an easier method compared to any other thing. So once you find your potential function, simply take three derivatives and see if it fits the vector field is given, right? So x component, y component, z component is indeed this one. So I give you a universal method to find the potential function for mainly two reasons. So one reason is a lot of vector fields, they are not as simple as this one where you can immediately see what the potential functions are. That's the first reason. Second reason, even if you can look at this function, you know what the potential functions are, sometimes the other people cannot see it. So I want to give you this universal method such that everyone can deal with every problem, okay? So the problem I gave you last week is to find the potential function for any given conservative vector. So let's look at a couple of more examples to give a better understanding of what it is. So let's look at the our two vector field. Okay, so this is the vector field. First of all, we can easily check if it is conservative or not. Right? So if this is my f component, this is g component, I only need to take the derivative as y, which is equal to 2y, which is exactly equal to g sub x. Right? So this is checked out. So it is a conservative vector field, which means I can rewrite this vector field as phi x phi y for its potential function. Right? And I'm looking for this phi function. Again, you can stare at this vector field for 10 minutes probably if you want to write down its potential function directly without going through the procedure we did last week. You can try to find it. It is not as simple as the example I gave you over there, but still you can try to do that. For instance, if I want the x derivative to be equal to 2x plus y squared, what do I want? I want to have x squared, definitely, right? I also want a y squared times x, such that when I take the derivative with respect to x, I'm getting 2x plus y squared. But also I have to make the second component phi, which means if I take the derivative with respect to y, I get 2xy, but I'm missing a minus 1 here. So what do I want to have here? Minus y and plus a constant c. That will do. Again, you can immediately write down your potential function, but you always want to check, especially if you're doing this in this way. It's really dangerous that you end up with a potential function you're super satisfied with your work. Always check by taking the derivative. Taking x derivative, I'm getting a 2x plus y squared. Taking the y derivative, I'm getting a 2yx minus 1. So this is indeed a potential function. Okay? So it is actually okay. This is a potential function. But as I said, I still want to go through the procedure because there are so many different vector fields. Okay? You still have some other ones you might not be able to see that immediately. Okay? In that case, you don't waste your time by staring at this vector field forever. Okay? You immediately go for the universal method. This universal vector is going to work for every single conservative vector field. With me? So I want to look for phi xy such that phi x is equal to 2x plus y squared. So this is my step 1. In step 1, I want to pair off the dependence of this phi function upon the variable x. So if I want to have this as my x derivative, I want a phi xy has to be equal to x squared plus y squared x plus a function or a constant. But this constant is depending on y, but not on x. So I have an additional function depending on y. Okay? So think about that. This is pretty natural. If I have a function depending on x and y, its x derivative is equal to 2x plus y squared, I have to write it in this x squared plus y squared plus a function. This function is regarded as a constant with respect to x. So very likely it will depend on y. All right? Because when we take the derivative, we regard all the other variables as constant. So when you find the antiderivative, you're still doing the same procedure, which means you hide the dependence on y when you do this first step. So that's why I have this constant depending on y to come out. In second step, I need to figure out what this constant function p depending on y is. So I'm going to take the derivative with respect to y in this format, and then I'm going to go back to make it equal to what is given in the very beginning. All right? So that's what we did last week. So phi of y on this function, I'm getting on this function, what do we have?
X squared plus
2yx plus p prime of y. Am I right? So I'm taking the derivative on this part. So taking y derivative. But I want to make this to be equal to what is given in the very beginning. All right? So in the very beginning, I have 2xy minus 1. So this is coming from the condition, okay, or the assumption here. So making these two equal, I have to make p prime y to be equal to minus 1 here, all right? I have to make a p minus p prime y to be equal to 1. Here I'm taking usual derivative because this is a function depending only on y, right? So you are taking the usual derivative here, which means p of y has to be equal to minus y plus a constant, all right? Minus y plus a constant. Plot these two steps together, I'm going to have phi of x, y has to be equal to x squared plus y squared, x plus p of y in the first step, but p of y is equal to minus y plus c in the second step. So this is going to be minus y plus c, okay? So if you have two variables, you can find this potential function within two steps by looking for its dependence on each variables individually, okay? In the first step, you already eliminate all the dependence on x. The second step, you find all the dependence on y. You put them together, you're going to get the potential function, okay? Here is what I highly suggest to you. You can always try to find a potential function in the very beginning, but don't waste your time on this method, okay? Because a lot of other vector fields, conserved vector fields, they can be way more complicated than this one. It's pretty hard to look at its vector field and see what the potential function is directly. The second step, you can do this logical. Okay, you don't have to worry about what how complicated the vector field is. Okay. Any questions? So now I want to give you one more practice in R3. So let's look at the vector field, which is equal to yz plus 2x, xz plus 1, xy minus 1. Okay. Still two layers of the question. Is this vector field conservative? And if it is, what is the potential function? Okay. What is the potential function? So David, let's see how whether this is conservative. We're working together, so not just this. Let's work together. So I want to look at this vector field and see if it is conservative or not, according to this system of equations. You with me?
Yeah.
Okay. So basically, this is my f, this is my g, this is my h, and I'm taking symmetric derivatives. So I want to have f y, which is equal to what?
Fy z plus 2x? Oh wait, just...
Well, I'm taking a derivative, right?
Yeah, just see.
So just z. And I want to make it equal to g of x, which is exactly z. All right? And I want to have f, what's this order here? Fz, what is f derivative with respect to z, David?
F with respect to z.
Which is...
that's just... Which one's 2 and which one's z? For the...
Oh, sorry.
Yeah, right now,
this is my z.
that
Sorry
z
for my
and the next one
confusion.
is that 2x or zx?
Oh, this is 2x. My z has a little bar here.
Okay.
Okay.
So that'll just make it y.
This is my, how do you write your z, by the way? How do you write your z?
Right, like that, like z and then cross it.
Cross it. That's basically the same,
Yeah,
right?
so that one didn't have a cross, so I'm like...
The cross was
The cross is z. Without cross is my shoe, right? Okay. And I want to make it equal to h of x, which is exactly x. All right? And the very last one I want to have is g of z. G of z is equal to, what is it?
Well, yeah, x.
X, and that's equal to h of y. Okay? So 3 equations, all of them check out. So this is indeed a conservative vector field. Okay? So in 3 steps, we're going to tear off the dependence on x, y, z separately. Again, you can stare at this for a couple of minutes and see if you can find its potential function directly. You can do that. This is not that complicated yet. You can still do it. But the point is, I want to practice this universal method. And in a lot of cases, if you think about the Y mathematics is powerful and applicable in everywhere. this is the reason, right? The reason is because we have this universal method to deal with functions, no matter it's coming from physics, chemistry, biology, or anything. If your mathematics skill is only depending on some potentially easy conservative vector fields, then your limit, your mathematics skill is going to be very limited. All right. So the power of mathematics is because of this universal method. It depends on essentially nothing of the function or the format of the function. So first step, I want to make phi of x is equal to yz plus 2x, okay? Where y and z are both considered as constant, right? So in this step, I'm essentially just dealing with a single variable antiderivative. I'm trying to find the antiderivative of with respect to x variable, all right? So what do you have? Phi has to be equal to x, y, z plus x squared. So I want everybody to be on board here, okay? So this is extremely important method you wanted to learn from Calc 3. How do you find the potential function, right? If you go to physics or chemistry, there are so many vector fields. There are so many conservative vector fields that you have to be able to understand what they mean and how do you find the potential function, okay? So I want you all to understand what we're doing here, essentially. So we are trying to find the antiderivative of this function where x is the variable, y and z are both constants. Are you with me? Questions? If you do have questions, you want to raise it right now, okay? So this is the part where x is the variable, y, z are both constant, which means I should have a constant dependent on y and z. So p, y, and z. So in the second step, I will be able to figure out the dependence of p with respect to what, right? Or with respect to x, depending on your step. So in the first step, I already found all the dependencies by x. So in the second step, I will be able to make phi of y to work. Again, you have to use the format or the function you get in the previous step, okay? You already find the dependence on x, so you want to stick with this expression of the function and take the y derivative, okay? So if I take the y derivative, what do we have? We have xz plus